Hello everyone and welcome to TLE Eliminators Codeforces post contest discussions for CF round 1052. How was the contest, guys? Before we get started, was B weird? Yeah, a little bit. Uh, could solve just A. Okay, B was harder than C. Really? I would say that B was easier. You just need to be more careful while reading the question. But okay. All right then, let's get into the problems. Um, okay. Before we get started, as usual, I'd like to remind you that we have self-paced courses for competitive programming available at our website, TLEeliminators.com. These courses are divided into 4 different levels based on what your current rating is and what your number of problems which you can solve. So if you're a complete beginner, you can join level 1. Meanwhile, if you're more experienced and you can solve maybe 3 problems in most div 2, then you can join level 4. All of these um, courses have more than 40 hours of recorded lectures, more than 100 practice problems, and as hints and video solutions for all problems if you get stuck, as well as doubt support available almost all the time. We also have a leaderboard so that you feel motivated to pursue your CP journey. So yeah, go ahead and check it out. All right, let's move on to the problems. Problem A, I think most people could do problem A. We call an array balanced if and only if the number of occurrences of its elements are the same. So for example, 1, 1, 3, 3, 6, 6, and 2, 2, 2, 2 are balanced. But here, as you can see, the example they've given, the number of ones and number of threes is different, so they are not balanced. Note that an empty subarray is always balanced, and you're given an array A consisting of n integers. Find the length of its longest balanced subsequence. Okay, so we simply need to find the length of its longest balanced subsequence. So let's break this down. Um, okay, so yeah, the questions were a bit on the harder side. Like A does seem slightly harder than the average A. B does seem slightly harder than the average B, but yeah, um, it's not that much harder. You just need to break down the problem. So let's have a look at what we can do here. So yeah, so we know that we need to find basically the longest balanced subsequence, right? So um, we need all the occurrences of a given element to be the same. So basically, we need to delete some elements from our array. We need to delete some elements from our array. We need to delete some elements from our array such that the array becomes balanced. The array becomes balanced, and we want to delete the fewest number of elements. We want to delete the fewest number of elements. Okay, so these are the things we require, and basically this means that each element each element can appear, let's say, either one time, right, or two times, or three times, and so on, right? So each element can appear either one time, two times, or three times in our balanced array. And what we can do here is basically um, for each element, calculate how many times it appears, how many times it appears. So we calculate the frequency of each element, calculate frequency of each element, and this can be done using a map. right? Of each element. Now, if we include this element in the array, so if we include this element in the array, a total of frequency number of times, then since all the elements which appear have to appear at least this frequency, then we can include all elements with frequency greater than or equal to the chosen element. Okay, so I hope this is clear. If we choose a given element, then if it has some frequency, then we can include all the elements with a frequency greater than or equal to the chosen element. So for example, let's say we choose a of I, to be in our subsequence, then we'll have a frequency array called frequency. So then for all elements which have frequency of x greater than or equal to frequency of ai, these can be included. Okay, so these can be included. And let's say there are total count such elements. Then our answer is count times frequency of ai, right? So each element can be included. The maximum number of times it can be included is the frequency of that element. So all the elements which are greater than or equal to that frequency will also be included, because we're trying to maximize the answer, right? And so we get our answer if we include this element as count times frequency of ai. Okay, if we include this element, our answer will be count times frequency of ai. So for each element, we simply need to count all elements which have greater than or equal to frequency as it, and then over all these cases we need to find the maximum. Okay, do above and find maximum over all the cases. Okay, find max over all the cases. All right, so let's just write the pseudocode for this. Pseudocode. We'll set our answer to 0. Okay, assume that we have frequency array. Okay, then for each ai, make a count. Let's say f is equal to frequency of ai. For let's say count is equal to 0. Then if frequency of x is greater than equal to ai, count plus plus, and then finally our answer will be equal to answer is the maximum of the old value of answer times count times frequency. Okay, basically we're saying if we include this element, we'll include all its occurrences, right? So f will be there. Then for all the values which have more than f frequency, we can include them as well. So count times frequency is the new answer we get when we include this element. And we're taking max of all the cases. Okay, so now since n is only up to 300, n square or even n cubed solution will work. So this big O of n squared solution will pass. However, we can make this into n log n. Make big O of n log n by sorting each element by frequency. Okay, by sorting the elements by frequency. Okay, and in that case we don't need to do this check manually. We just see how many x are there count how many x are ahead of me in O of 1, right? So in that way, we only need time for sorting. So the time complexity gets reduced to n log n. All right, if we do that optimization. So let's have a quick look at the code for this problem. Okay, so we take in n and we have a vector a of n. Then for each value of x, we take that in. And what I'm doing here is basically, since each value goes up to only 1 to n, right? Each value of a of I only goes up to 1 to n. As you can see, a of I goes up to 1 to n. The way I'm solving it is I'm simply storing it in an array A, and then I can do a of x plus plus. Okay. Now by sorting this, I have sorted all the elements by frequency. I have sorted all elements by frequency, right? So that's what I said. We are sorting all the frequencies of all elements, right? So that we can do it in O of n log n itself. So when we are sorting all the frequencies of all elements, we start with an answer of 0. And for each element, if we take that element, our answer is the maximum of answer times n minus 1 times a of I. So this is a of I over here will be the frequency, right? Frequency of I, and n minus 1 is the elements with greater than equal to frequency, right? So including myself and all the frequencies which come ahead. Since we have already sorted by frequency, this works, and then we can print out the answer. Obviously, it's not required to optimize this much. Even a big O of n square or n cube brute force will solve it. But this is the n log n solution to the problem. All right. Raja, you're somewhat correct, but not completely. Anyways, let's move on to problem B now. Are there any doubts in A? If there are any doubts, please drop it in the chat. I do know that's slightly more complicated than usual A, but I guess most people would have solved because even if you have an n cube solution, it will still pass. But this is the n log n solution. So if you could not come up with an n log n solution, go through this. It's a pretty normal greedy idea. Okay, so let's move on to problem B. Okay, you're given n sets S1, S2 up to Sn, where each element is an integer between 1 and m. You can choose some of the sets such that every integer between 1 and m is included in at least one of the chosen sets. Okay, you have to determine whether there exists at least 3 ways to choose the sets. Okay, and then they've given some constraints like the sum of n does not exceed 10 power 4, sum of m does not exceed 10 power 5, and sum of L, where L is the total number of elements in all sets, does not exceed 2 times 10 power 5. Okay, so let's just write down our constraints here. Problem B. Okay, given n sets, can we choose some of them such that their union has all elements 1 to m. So I'm just summarizing the problem in at least 3 different ways. In at least 3 different ways. Okay. And to be honest, your combinatorics just needs to be a bit sharp for this. It does look a bit daunting because the input format is also a bit daunting and the constraints are a bit daunting, but it's actually pretty simple. So our constraints are given as n less than equal to 5 times 10 to the 4, m less than equal to 10 to the 5, and L, which is the sum of all elements, number of elements in all sets, is less than 2 times 10 to the 5. Okay, this is the given constraints. All right. So how do we go about this? Let's just take an example. Okay, so let's take an example for a Yes. So we have this example one, because these questions are usually easier to solve with examples. In this, set 1 has the values 1 and 2, set 2 has the values 1, and set 3 has the value 2. Okay, and the total um and the total m, so the total number of elements or across all of them, m is equal to 2. Okay, so now as we can see, there are three ways to choose the sets. For example, we can choose this, or we can choose this, or we can choose this, or there's another way we can choose these two and these two, and still their union will still be equal to all the numbers from 1 to m. So definitely there are more than three ways. Okay, therefore more than three ways. Okay, let's take another example. So here we have, let's say, set 1 equals 1, 2, 3, and set 2 equals 4, 5, 4, 5, and set 3 equals 6, set 4 equals 7, 8, 9. Okay, 7, 8, 9, 10, and m is equal to 10, right? So here we have no other option but to choose all the sets, right? We have no other option but to choose all the sets, and that's why the answer is no, because there's only one way to guarantee a union of m, only one way. Okay, so let's see an example in which there are two ways as well. So I'll just write my own example. Uh, Example, let's say our set 1 is 1, 2, 3, our set 2 is 4, and our set 3 is 1, comma 2. Okay, so now in this case, we have to choose this set. We have to choose this set, but this set is optional, right? This set is optional. If we choose it or if we don't choose it, doesn't make a difference. So the total number of ways is two ways. Okay, and that's why in this case also the answer will be no, since it's not equal to three ways or more. But yeah, so in this case the answer will be two ways. Okay, so what are the observations we can make here from this? Well, the first thing which you get by seeing this test case directly is that if some value does not occur, right? If some value, observation one, if some value from 1 to n, from 1 to m does not occur, does not occur in any set, in any set, then there are zero ways to do it, right? Then there are zero ways to do it. Then our answer is no. Then our answer is no. Okay. Now what is our second observation? Um, if some value, some value occurs in exactly one set, okay? If some value occurs in exactly one set, then we must have to take that set. Okay, we must take that set. Take that set. Okay, right. So we'll call these sets as the sets which have unique values. Okay, the set which if there's some value which occurs in exactly one set, then that set we must take it, and let's call these special sets. Okay, special sets. Basically these are the sets which have to be taken. Okay, and we can think about the fact that this is probably the key to our problem, right? These are the sets which must always be taken, or sets that always have to be taken, always have to be taken. Okay, so let's just take an example in our mind where let's say we have S1, S2, S3, S4, S5. Okay, um, So let's say that S1, S2, S3, S4, and S5. Out of these, S1, S2, and S3 must always be taken. Okay, so these are special sets that always must be taken. Always taken. All right, all these three. Let's say they have some value which does not occur in any of the others. Okay. Meanwhile, these two sets, they may or may not be taken because every value which is there here is also there in some other set. Okay, it's also there in some other set. Let's say, so something like this. Okay, so the values which occur in these are already present in some other set. Yeah. Okay. So then these sets are kind of redundant and we can choose them whether or we are not we want, right? So let's say the what are the options we have, right? So one of the options is we can choose either S4, right? Or we can choose S5, right? Or we can choose both, right? So even if there are two such sets, which may not always be taken, we can choose either one of them or the other one or both of them, correct? So if we have some set, if we have some two sets which may not be taken, which don't have to always be taken, which don't always need to be taken, or two sets which are not special, or two sets which are not special, which are not special, that already gives us three ways. Okay, that already gives us three ways, gives us three ways. Uh, at least we have at least two sets, at least two sets, right? That already gives us three ways. The first way is choose set one. The first way is choose everything. Way one, choose everything, choose everything. The second way is choose everything except set one, choose all except set one. And the third way is choose all except set two. Okay. And since we know that it's not required for S1 or S2 to always be chosen, then choosing everything except them makes sure that we have everything from 1 to m, and still we are finding three different ways to do it. Okay. So if there are two non-special sets, then we have three ways. Okay. What if there's exactly one special set? And we already saw this case. So let's say S1, S2, S3, S4. Okay. So this one is special and S4 is not special. Okay. So special, 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 not special. In this case, we have to choose these, and we can or we cannot choose this. So this is two ways, right? If we can or we cannot choose this. So this will simply be two ways, and so the answer will be no. Okay. So let's go ahead and write down our observations again. So summary. If some value doesn't appear, then answer is no. If some value appears in exactly appears in exactly one set, then that set is called special. That set is special. Count the non-special sets. Count the non-special sets. If this count is greater than equal to 2, then our answer is yes. Otherwise, if the count is less than 2, our answer will be no. Okay. And that's it. If the non-special sets are greater than equal to 2, our answer is yes. Otherwise, the answer is no, simply for this reason that if there are at least two non-special sets, then we have three ways. Choose everything except the first non-special, choose everything except the other non-special. Right. And if we have only one, then there'll be two ways. And that's how we get this problem down. Right. So I hope this is clear. Let's see. Why so less audience today? I don't know. Maybe because it's a bit later. Not sure. Okay. How many did you solve? Okay. right? Okay. So is this clear, guys? The time complexity for this would be um, simply big of n or big of n log if you use maps. In real context, I prefer to use maps when possible because you never know when you can be attacked with hashing. Like unordered maps use hashing, so it can be subject to collisions. So the way I've implemented is using maps. So for each element, I'm counting which sets it appears in. Okay, so for each element in each set, I'm like, okay, this element appears in these many sets, right? So the time complexity of this is this map stores total big of L values, okay, and so the time complexity of this is big of L, okay, and then for each value from 1 to m, I'm checking if okay, since I'm doing a set access, then this will be big of L log m, right? And then for each element from m, I'm checking if it appears exactly once. So you can say another m log m, right? And then I'm counting how many unique sets are there, and I'm printing yes or no based on that. So the total time complexity will be roughly big of L log m itself, right? So this is the total time complexity if you use maps to implement your answer. Okay, so I'm using a map here. I'm using set as well to keep track of the count. Obviously, you can do it without them. You can do with hashing. And if you implement it properly, that would be big of n. So yeah, this is the code. Go through it once. Okay, we'll move on to the problem C now, right after a 1 minute break. All right, let's start with the problem C now. Wrong binary search. To be honest, this was a very nice problem. I personally liked it. So let's get to it. Wrong binary search. Okay. You're given an integer n and a binary string of length n. We'll define a following pseudocode on a permutation. So basically, we're doing a binary search over here, but each time we're choosing a random integer between L and R as a midpoint, and then we're doing a standard binary search. Okay, so basically so pseudocode given here is basically binary search with random midpoint, right? Binary search with random midpoint. Okay, so we have basically L equals 1, R equals n, while L is less than equal to R. Um, M is random number between L and R index, right? And then we're compare with PM. So if PM is equal to our target, right, which is equal to our target X, then we can just return M. Otherwise, we change our binary search bound. So like standard binary search, right? Otherwise, if PM is greater than X, now we need to move towards the left half of our binary search. So what we'll do is R equals M minus 1, else L equals M plus 1, right? So this is a standard binary search, except what we're doing is we're choosing a random number between L and R, okay? And what is the question? It says that we call integer X stable if and only if this function find is always not undefined, okay? So undefined means if it's not found. Okay, so if it does not find it, it will return undefined, right? So if it can always find your value, no matter what random values it chooses, always find no matter what the random value is chosen. Okay, always find some x, no matter the random value is chosen, no matter the random value chosen, then it's stable. Okay, then x is stable. That's what the definition is. And we can, yeah, so what we're saying is, given a permutation, we need to rearrange the permutation such that I is stable if and only if the input si is equal to 1. Okay, so we're given some input strings and we have to print a permutation of that length, and it should be stable if si is given as 1. Okay, if si is given as 0, it should not be stable. So basically, according to the input, according to the input, according to the input string, input string, the SIth element, the SIth element, uh, or the ith element should be stable, should be stable if and only if SI is equal to 1. Okay, so that's what the question is asking us. Yeah, actually, I'm at my home setup, so the voice isn't that great. Anyways, so let's move on. What are the time complexity in this? So let's just see the constraints. N goes up to 10 power 5, so we need standard big O of n constraints. Okay, so constraints big O of n or big O of n log n solution is required. Okay, solution required. Okay, so how do we do this? What observations can we make? Okay, so when is an element not stable? So clearly we should understand when an element is stable, when an element is stable, is stable, and when it is not stable. Okay, when it is not stable. Okay, so when is an element stable and when it is not stable? Well, let's try and see. So given our LNR, what does the random binary search do? Okay, what does the random binary search require? And if you have studied binary search, so obviously a prerequisite to this question should be knowing normal binary search, right? If you have studied binary search, the main requirement for binary search is that in this range, all the values should be monotonic. Okay, in this range, all the values should be monotonic. Okay, this is a standard requirement for binary search. And more specifically, if you're searching for some value x, okay, if you're searching for some value x, let's say this is the x which is equal to 5, okay, and let's say there's some values before it, like, or maybe this x is equal to 4, and there's some values before it like 3, 1, 2, and there's some values after it like 7, 5, 6. Okay, so these are the values before it, and these are the values after it, and we are searching for x equals 4. Okay, so now the main observation is that um, if we can choose any random middle point, right? So this can be chosen as a middle point, and then this can be chosen as a middle point, this can be chosen as a middle point, and based on that, the array will get restricted, right? So basically, what we need is that no matter what middle point, if it is before x, it should be smaller than x, and if it is after x, it should be greater than x. Okay. So if you think about it, you realize this. No matter the m chosen, no matter the middle point chosen, the middle point m chosen, if we want our binary search to succeed in all cases, all values, all values before x should be less than or equal to x. Okay, should be not less than equal to, because the permutation should be less than x. Okay, so all these values should be less than x, and all these values should be greater than x. So now if in our example you see, for example, if we choose 1, okay, if we choose 1, Now we know it is smaller than 4. So it will restrict our binary search to this range. Similarly, if we choose 2, it will restrict our binary search to this range. Next time we choose 5, it's going to restrict our binary search to this range and correctly find that 4 is in this position. Okay. So what if this was not the case? What if we had a 5 over here, let's say, and we had a 1 over here in a permutation? Okay. Now what would happen? Now 4 would not be stable. Now 4 would be unstable. So for example, um, if I choose, let's say 5, instead of like I can choose any middle I want, right? Middle is a random number. So what if I chose 5 as my middle? Now since this is larger, I will restrict my binary search to this range. And I'm going to end up missing 4 completely, right? I'm going to end up missing 4 completely. So the condition for stability is this. All values before x should be less than x. All values after should be greater than x. Okay, all values after should be greater than x. So this is the condition for a given element to be stable. Okay, so is this much clear, guys? All values before x should be less than x. All values should after x should be less than x. So for every s of I equals 1, so for every s of I equals 1, this gives us some observations. First of all, let's say our answer is permutation of I, right? First of all, answer of I will equal to I, right? So because all the values greater are afterwards, all the values less are before. So answer of I must be equal to I because it's a permutation. Now values from 1 to I minus 1, 1 to I minus 1 must occur before, must occur before, and values uh, one sec, there's some issue with my pen, just give me a second. Okay, and values greater than x, greater than I, and values, let's say I plus 1 till n must occur afterwards, right? Must occur after, right? Okay, so now what if we want to make it unstable? Okay, so let's say our given string is like 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0. Okay, this is the given s. Okay, and over here you can see n is equal to 4 plus 4 plus 3, which is equal to 11, right? N is equal to 11. So now what we know already is that our final answer array will be looking something like this, right? So let's say blank, blank, blank. Here this should be equal to 4 because that's the only value you can go here. Again, blank, blank. And then here this should be equal to 7. And then again a few blanks, right? And this will be our array, right? So now we know that to fill these blanks, we need the values 1, 2, 3 some in some order. Similarly, we need the value 5, 6 in some order. Similarly, to fill the blanks afterwards, we need 8, 9, 10, 11 in some order, right? So now what is the order? The order should be such that all of these become unstable. Okay, so all of these should become unstable. All of these should be unstable, right? Unstable. And the easiest way to do this is to keep the smallest element in the end. Okay, so we can keep it instead of 1, 2, 3. We'll just write it normally like 2, 3, and then 1. Okay, similarly here we can write 6, 5, and here we can write 9, 10, 11, 8. And what happens when we keep the smallest element is in the end is, let's say we are looking for any other element, then if we try the smallest element, we will start searching ahead, which will make our binary search go wrong. Similarly, if we're looking for 1 itself, then if we come here, we'll start looking behind, so it'll go wrong. Okay. So basically, in all the islands of zeros, we need to keep the smallest element in the end, and rest of them can be shifted one back. Okay. So for each position, so what we have concluded for each position where s of I is equal to 1, then answer of I should be equal to I. Answer of I should be equal to I. For positions or for blocks of 0, right? For blocks of 0, for blocks of zeros, the smallest one, the smallest one of the block can be shifted to the end. That is one way to construct it, and it's the easiest way. can be shifted to the end. Okay. So we're trying to make it unstable, right? So we can make the smallest number in the end. And that is one way to make it unstable. Okay. Now the only thing remains is what if the block size is 1? Okay. What if the block size of 0 is 1, right? Let's say um, block size of 0. Like blocks of 0 basically means a subarray of continuous zeros. Okay. So block of 0 has size 1. Then what? Right? Then what? And for example, let's take an example string like 1 1 0 0 1 0 1 1. Okay. So in this n is equal to 8, and the fixed values will be 1 comma 2. These two will be not fixed. Then it will be 5 not fixed, um 7 and 8. Okay, so now in these not fixed, what we can do is we know we need to fill it with 3 and 4 somehow, and we can move the smallest one to the end, so we'll get 4 and 3. Okay, we'll get 4 and 3, but in here there's only one element, so we can't move the smallest to the end, right? The smallest is staying at the same position, and we have 6 over here. But then this will become stable. Okay, this becomes stable. Why is it stable? Because everything before it is less, everything after it is larger, right? But we did not want it to be stable. So if there is a block of size 1, right? If a block of 0 has size 1, the answer will be no. In all other cases, the answer will be yes. And we simply need to move the smallest element of each block to the end. Okay. So that's it for this question. Uh, Madhav did not get it. So can you tell me what exactly you're not getting? I'll just repeat what I said. So what I'm saying is basically for a binary search to find a given element, all the elements before it should be less than it, and all the elements after it should be greater than it. Okay, and the reason for this is because if our like middle point can be chosen randomly, right? So if the middle point goes before it, it should only come to smaller values. If the middle point goes after it, it should only come to larger values. In that only guarantees that the correct range occurs. Okay, that guarantees that the correct range occurs. So now, if since that condition is there, we know that every point which is a 1 must be equal to itself. Like if the, for example, this is at position 4, so we know that the value at this position should be 4 itself, because since all the larger values are after it, all the smaller values are before it, so only one value remains, which is 4 itself. Correct? Similarly for this will remain 7 itself. Now the elements between it should be less than 7 and greater than 4. That means these can only be 5 or 6. These can only be 1, 2, 3 in some order, and these can only be 9, 10, 11, and 8, 9, 10, 11 in some order, right? Now we need to find some order to put these in so that they become unstable. Fine, that's what where basically our logic is. Can we write the unstable numbers in reverse after setting the stable values? Well, let's try it. Um, so let's say all are zeros, right? And then we have 4, 3, 2, 1. We wrote it in reverse. So now if we're looking for a 1 and we chose this as a middle point, then we can simply go outside, right? So this won't work. Similarly, if we're looking for a 2, again, we can go here, 3 again here. If you're looking for a 4, we might want to look ahead of this. So yeah, you can simply write the unstable ones as reverse also. So that also works. You're right. We can write unstable ones in reverse. We can write unstable ones in reverse. That's another method. Does the same thing. Blocks in reverse also works, right? Because the smallest one is going to the end. So this also works. Okay. Also, unique says that 3 to 1 will make 2 stable. How will 3 to 1 make 2 stable? Let's say we have 3 to 1 and our binary search chooses the midpoint of this. Okay, a binary search is searching from L equals 1 to R equals 3. So it's searching in this range and it chooses this midpoint. Okay, now it says that 3 is greater than 2. So it's going to search in this empty range now. And since the range is empty, it will return undefined, right? So that is not stable. That does not make 2 stable. By the way, Raja, one thing is there that if our input is something like this, okay, if our input is something like this, um, 0, 0, 0, 1, right? Right? This is also valid. This is also valid, okay? So it's not that if exactly 1, 0 between two ones, that's correct. But if one not at 1 or n minus 2, that you need to be clear. Basically, this block should be of size 2 or greater. So yeah, each block of zeros, each block of zeros should be greater than equal to 2 size. Okay, so that's what we need. So yeah, you're correct. Also, Unique, I think you're wrong because 3 to 1 is not stable. In 3 to 1, if you want to find 2, then that will go to, imagine we choose the midpoint of 3, then it will become unstable, right? It will not find its target. Okay, so I hope everyone understood this question. If you have any doubts, just put it in the chat. Right, so let's have a look at the solution code as well. So the way I did it was I took n and my string, I filled it with a normal permutation. So iota fills the values of answer with 1, 2, 3, 4 till n, right? So I hope you know how iota works. This is just to fill it with like 1, 2, 3, 4 till n, okay? This function does it for us in C++. Now we're setting possible as true, and if s of I is 0, then what I'm doing is I'm swapping it with the next element, right? Why am I swapping it with the next element? Because I want the smallest one to be in the furthermost, right? I want the smallest one to be in the furthermost. That's why I keep swapping it with the next element, which is 0, right? And if there is no 0 adjacent to me, if like left of me also there's no 0, right of me also there's no 0, I will set as possible equals false. Okay, so that's all I'm doing here. Finally, I output yes if it's possible, and I output the values. Otherwise, I output no. Go through the code. All this is doing is it's swapping the smallest element to the end of any block. Okay. So for example, if this is all ones, so this is just 1, 2, 3. This is all zeros. So the smallest element 1 has been moved to the end, right? 1 got swapped with 2, then 1 got swapped with 3, and so on. The smallest element in the end. Here there's exactly 1, 0 over here. So the answer is no, and so on. So that's the idea for this. Yeah, for all s of I equals 1, you can fix the value to be I plus 1. That's correct, yeah. I am first just directly creating the permutation. So I'm directly filling each I as 1, 2, 3, 4, 5 till n. And then after that, the ones which are zeros, I'm swapping them. So you can do it either way. But anyways, for the ones which are zeros, you need to fill it in some order, right? Okay. So that's all for problem C. Any doubts, please put it on the chat. The time complexity for this is simply big O of n. Okay. Time complexity is big O of n. Okay. So we'll move on to problem D now. So before discussing D, I would like to mention that my solution for D1 versus my solution for D2, I feel like my solution for D2 is more clean. So I'll explain both at once, right? I'll explain both at once since anyways I have to explain D2 as well. So I'll explain both at once and then you can see the code for both of them, right? Since obviously D2's solution will also solve D1 solution. So yeah, let's have a look at it. Okay. So the problem says we are given two integers L and R. We have to create an array equal to all the values from L to R in the number line. So basically like L plus 1, L plus 2 till R. Okay, so we create array. problem D, right? Given L and R, we have basically an array of all the values, two arrays of all the values from L, L plus 1, L plus 1, L plus 2, all the way to R. Okay, so this is our first array. Similarly, we have another array B, which is also L, L plus 1, L plus 2, all the way to R. Now, our job is to reshuffle this array. Okay, our job is that we can shuffle this array, right? Shuffle this array in any way we want, such that the sum of the values of ORs at all positions is maximized. Okay, so sum of value of OR at each index is maximum. Okay, so that's what our goal is going to be. And in our easy version, we are given that L is exactly equal to 0, right? L is exactly equal to 0, and R is less than 2 times 10 to the power 5. Okay, so we're given that L is equal to 0, R is exactly equal to 2 times 10 to the power 5. Okay, R is exactly less than 2 times 10 to the power 5. So we're given this constraint. Fine. And we need to first print the maximum value, and then we need to print some rearrangement of A which satisfies the given conditions. So let's have a quick look at the test cases. So let's have an look at the examples. N goes up to 10 power 5. So obviously we need big of n log n some kind of construction, right? I guess system testings are over. Let's just check. Right, cool. Okay. So let's take the first example, 0, 3, right? L is equal to 0, R is equal to 3. That means our array is equal to the numbers 0, 1, 2, 3. And our second array is also equal to the numbers 0, 1, 2, 3, right? Now we have to rearrange this. So now since we are dealing with bitwise operation like bitwise OR, it's best if we look at it in binary format. Okay, it's best if we look at it in binary format. So let's write the array A, and let's write the array B. Okay, and the array is simply 0, 0, and then like this. Right. So right now this is the most unoptimal because it's simply all the ORs are basically canceling out kind of, right? And we want to rearrange it in a fashion such that the OR is maximized. Okay. So let's look at their solution. Their solution is to write 3, 2, 1, 0. Okay. So what they're doing is they're pairing this with this, right? They're pairing this with this. They're pairing this with this, and this with this, right? So that's basically what they're doing. And if you observe, what this does is basically here these two 1 bits are on, right? Here these two 1 bits are off. So it turns this bit on, it turns this bit on when you do OR, right? When you do OR, these two bits get turned on. Similarly for the pairing like this, right? This pairing also is the same. Now what about the pairing here? So this one gets paired with this, and as you can see, this and this, we can turn this 1 bit on. Similarly, we can turn this 1 bit on, and basically we're pairing with like its complement, right? Here also we're pairing with like its complement because that ensures that our OR becomes maximum, right? So let's just pair it up and see what happens. So we pair this with this, and our value becomes 3, right? So 0, 0, 0 or 0, 1, 1 is equal to 3. Similarly, 0, 0, 1 or 0, 1, 0 is equal to 3, right? And this gives a very nice idea for powers of 2. So if your number of elements is equal to some power of 2, you get a very simple and clean solution. So let's just write all the values up to a power of 2, right? So let's say it's like this. Right. So let's pair them up all up to powers of 2. And what we get is basically, we can pair this with this basically, right? So in that case, the OR is equal to 1, 1, 1. Similarly, we pair this with its complement. So its complement will be something like this. This will get paired with 1, 1, 1. And then this will get paired with 1, 0, 1. This will get paired with 1, 0, 0. And basically, the idea is that the complement always exists. Okay, the complement always exists when the number of elements are a power of 2. And so our answer becomes basically 1, 1, 1 plus 1, 1, 1 plus 1, 1, 1, and so on. And basically, total all these power of 2 times, we're adding this value of 1, 1, 1. Okay. Instead of jumping straight to the observation solution, Anurag, I did explain one test case, and also usually when you see the PCD, it's best if you have already read the question and then you're doing it, right? I don't see much point in seeing the PCD if you have not even read the question. So yeah, um, and I believe that if you have read the question, this observation would be pretty straightforward. But okay, I'll try to keep in mind what you said. Okay, so okay, so and basically what I'm trying to observe here is pretty simple. That if your values count up to a power of 2, right? So this goes from 0 to 7, which is 8 minus 1, right? Each value of bit appears both as 0 and 1. Like for example, 0, 1, 1 appears. Similarly, 1, 0, 0 appears, right? And similarly, 1, 1, 0 is there. Similarly, 0, 0, 1 is there. So when you pair it up with a complement, you get all the bits as 1, which is clearly the maximum possible, right? So that's what we're observing here. So observation, pairing with complement works best. Pairing with complement works best. Okay, for powers of 2. And also this is a constructive problem, so there's not much explanation. It's more like a series of observations which you must make. But yeah, okay. So now what if your number is not like a neat power of 2? What do you do in that case? Okay. So let's say our number is something like um our L is equal to 0, obviously, for this case, and our R is, let's say, equal to, let's say, 5. Okay, so all the numbers from 0 to 5 we need to check. And so let's write it down. So we have 0, 0, 0, 0, 1, 0, sorry, 0, 0, 1, 0, 1, 0, 0, 1, 1, which is 3. Then we have 4. Then we have 5. Okay. So how do we pair these up? Now, if you see, some missing values which are there, which are not there in the array, are basically the values that were the complements of these two. Okay, these ones complements are not there. So basically 1, 1, 0 is not there and 1, 1, 1 is not there. So we can't use them, right? However, we'll try to use the ones which we can. So for example, 0, 1, 1 is here. We can see that its complement is 1, 0, 0. So if we pair these two, right, if we pair these two, like 0, 1, 1 gets paired with 1, 0, 0, 1, 0, 0 gets paired with 0, 1, 1, right? So their OR will be equal to the maximum possible, which is 1, 1, 1, 1, 1, 1. Okay. Similarly, this and its complement exist, right? This one and its complement exist. And if you pair it up with 0, 1, 0 and 1, 0, 1, if you take the OR, if you take the OR will be 1, 1, 1 and 1, 1, 1, right? So we have this, these values are fixed. Okay. Now in the remaining two, we have no other option but to pair them up with each other. Okay. Now in the remaining two, we have no other option but to pair them up with each other. So we're going to pair this with 0, 0, 1 and pair this with 0, 0, 0. Okay. And if you see, the OR of these will again be 0, 0, 1, 0, 0, 1. And this will be our final sum. Okay. And this gives us the answer to this test case. Fine. So I hope this part is understandable. Let's take another example and try it. Okay, let's take another example and try it. And let's take another example and try it. Let's say L is 0, R is 4, and we have 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. How do we pair it up in this case? Now again, if you see, these two are complements, so their complements exist. So all we can write is simply pair this with 1, 0, 0 and pair this with 0, 1, 1. We get a maximum OR of 1, 1, 1. Okay, we get a maximum OR in these two cases. We're basically preparing them up greedily based on the fact that we want to make all the ORs into ones, right? So each one bit which appears, we were trying to pair it up such that they don't get lost, right? So now what we do with the remaining ones? What do we do with the remaining ones? And we can see that one way to pair it would be like this, where we just pair these two, and we can leave 0 to be paired with itself since it has no bits, right? So we have 1 0. We pair this with this. We pair this with this, and we get an OR of 0 1 1 0 1 1 0 0 0. Okay, so this is the rough idea which is going on right now. So like Anurag said, try to look at the examples and find the observation. I'll write down another example for you so that you can try and see what the observation here is. Um, so let's take one from the given test case itself. So maybe 0 to 9, or maybe let's try like a large test case. Okay, so let's try 0 to, okay, let's try 0 to 9 itself. Okay, so L equals 0, R equals 9. L equals 0, R equals 9. Let's write down all the elements: 0 0 0 0 1 0 0 0 1, 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 1 0 1 1. Then we reached 8, and now we reached 9. Okay, so now in this test case, how do we pair up? Again, as you see, this one, and it has its own complement. This binary number also has its complement. So it makes sense to pair them up, right? It makes sense to pair them up, and we get an OR of 1 1 1 in here, OR of 1 1 1 1 here, OR of 1 1 1 1 here, and OR of 1 1 1 1 here. Okay. Now the remaining ones do not have their complement that cleanly. So how do we pair the remaining? Okay, how do we pair this 0 1 0, for example? So now what we can do is basically, if you observe this bit, it is all set to zeros, right? This bit is all set to zeros. So let's not care about that. And let's just care about the complements excluding this bit. Okay, let's care about the complements excluding this bit. So now again, as you can see, excluding this bit, we have that these two are complements. Okay, these two are complements. These two. Similarly, these two are complements again, right? So if we pair them up, what will happen? We can pair this with, let's say, 0 1 0 0, right? Sorry, 0 1 0 1, right? And we pair this up with 0 1 0 0. We pair this up with 0 0 1 1, and we pair this one up with 0 0 1 0, right? So in all of these cases, we get 1 1 1 as our answer. Okay, 1 1 1 after doing the OR. And basically, we're saying that since this first bit is all zeros, let's only compare the remaining bits and take complement of those bits. Okay, now we have these, and here we can say the first three bits are all zeros. So now we'll just compare the remaining bits and take complement. So basically, here it will be paired with 0 0 0, and here it will be paired with 0 0 1, right? And as you can see, the OR is equal to simply 1, right? And add all this up, and we get our maximum sum. Okay, so I hope the observation is clear now. We are pairing each element with its complement when possible, right? Pair each element greedily with its complement. So from largest element to smallest, obviously, since the largest bit is the one dominating, right? Like this bit is the one which is more important than a later bit. So from the larger bit, we are pairing with its complement. And then once that bit is used up, we delete that bit basically, and we look at the remaining bits. Okay, so pair each element greedily with its complement, complement, and after that, what do we do? Pair each element greedily with its complement, and then if the complement does not exist, right? That will happen if, for example, like at this value, the value 1100 does not exist because it's outside this range, right? 1100 is outside the range. So what we'll do is we'll simply drop the first bit and we'll look for 100 instead. And as you can see, 100 does exist. It exists here, right? So that's why these two are getting paired up. If the complement does not exist, drop the leading bits, drop leading bits. Like we should not care about the complement of leading bits. The leading bits can be the same. Leading bits can be same. Bits can be same. Let me just write it like this. So these are the observations we're making purely on like what we observed, right? Leading bits can be same until some complement exists. Okay, until some complement exists. And that's the main idea for this, right? We're trying to find the complement of each number and we're trying to pair them up. And the reason we're doing this is because this is setting all the bits to 1 and not losing any of the bits, right? So we can get the maximum sum. And when it is not possible to set this bit to 1, then we're just making sure that the others get set to 1, right? So it's a bit hard to prove this, but I hope it makes intuitive sense. In a contest, like I'm also not very sure how to prove this, but yeah, the intuition is pretty clear, and I think you should be correct why this works, right? Okay. So now there are many ways to implement this. I will tell you two ways. Okay. So method number one, two ways to implement. So obviously there'll be many ways, but these are two ways which I did for D1 and D2. Okay. Two ways to implement. One of the methods works directly for D2. The other method does not. But yeah, one of the ways to implement is that if you do observation here, right? If you see this power of 2 minus 1, so this is equal to 7, which is 2 to the power 3 minus 1, right? So 8 minus 1 over here, 7, right? So now as you see this value 7, um, observe that like this is 8 and this is 7, right? So what is happening is 8 and 7 are getting paired up, right? 8 and 7 are getting paired up. Similarly, 9 and 6 are getting paired up, right? 6 and 9 are getting paired up. And around the power of 2, basically the pairings are happening, right? So once this stops, we go to the next power of 2. The next power of 2 is simply um 4, right? We go to 4, and now 4 and 3 get paired up, right? And these two get paired up, right? That's basically what's happening. These two get paired up, these two get paired up, right? And then after that, once this is used up, we go to the final power of 2, which is 1. So 1 is obviously 2 to the power 0, and these two get paired up, right? So we are basically finding a pattern so that we can construct this. And pattern 1, which we can use is find the largest power of 2, find the largest power of 2, right? Let's say it's at position I. Let's say it's at position I. So basically what we'll do is we'll pair I and I minus 1. Then the next thing we'll pair is I plus 1, I minus 2, I plus 2, I minus 3, and so on. We'll pair these values. Okay. So around the power of 2, we're pairing front and back. So if you observe, this works for all the examples. Like even for the examples where it was only just, for example, 8 elements, right? So here the largest power of 2 is 4. And then we do pairing like this, like this, like this, and like this. Right? So that's basically how we're doing the pairing. Around the power of 2, we're trying to pair them up, right? So the value which is equal to power of 2 will be paired with value power of 2 minus 1. Power of 2 minus 2 will be paired with power of 2 plus 1, and so on, right? So it's like a mirror around that power of 2. Right? So these elements will be paired until um, until, for example, I plus x goes bigger than n, right? Once it goes bigger than the boundary of n, then we can stop this, right? So for example, when we are doing this pairing, here it becomes bigger than the boundary. This one will become bigger than the boundary. That means that this value does not exist. So we can stop this and we can start pairing from a smaller power of 2. We can start pairing from 4, right? Here we started from 8, then we can start from pairing from 4, right? So then stop until this happens, then stop and start pairing from smaller power of 2. And basically, we're making the observation that these pairings are symmetric around powers of 2. And that is clear because complements are also symmetric with respect of power of 2, right? Complements. Basically, the idea is that, or the pattern is that, complement each number, if you symmetrically take out with the power of 2, then it will be its complement. So, for example, if you have a power of 2 like this, the next value will be like this, the previous value will be like this, right? And then the previous value to this will be like this, right? So, around the power of 2, symmetrically we get the complements. So if you imagine a mirror here, it's like it's giving the mirror to its complement, right? So complements are symmetric around powers of 2. Okay, around powers of 2. So basically that's the idea being used here. And if you implement this pairing correctly, you just need to be careful about the implementation. This will pass D1. Okay, so this observation passes D1. This passes D1. I'll show you the code. The time complexity for this should be the time complexity of this, depending on how you implement it. It can be implemented even in big O of n or big O of n log. Doesn't matter. If you use maps or something to keep track of powers of 2, it will be n log. So I'll show you my implementation for it. Um, okay. So this function just finds the largest power of 2 less than equal to a number. Okay. Now we have our answer array, which is going to be all the values from L to R. Right. We're storing all the values from L to R in this. And for each value, we're storing its position. Okay. So this is the final array. This is the final array A, which has all values from L to R, which has all values from L to R. And this is the position of a given value. So this is a map. This is a map for a given value. It stores the current position. Stores the current position. So these are helpful map which I made. So this is why it becomes n log n for my code. But if you think about it, you can implement it in OFN. It'll be just a bit more complicated. Okay. So now also we have a bool array called done. So if a value is done, I don't want to visit it again, right? So when I'm reflecting about, let's say, power of, like I did these values around 8, right? So now when I start reflecting around 4, I do this one, I do this one, but then I don't want to reflect like this. I don't want to reflect like this. I don't want to take this complement. So that's why I have a done to make sure that everything which has already been assigned a pair should not be assigned again. Okay. So now I start with the largest power of 2 less than equal to R until it is greater than L, or in this case, L is always 0. So until it is greater than 0, I divide my power of 2 by 2, right? And I'm trying basically all the power of 2 by 1 by 1. If this position is already done, I continue. Otherwise, I start at this position. So I equals this power of 2 position. J equals power of 2 position minus 1. Okay, so I equals the position of this power of 2. J equals this minus 1. And what I do is simply I plus plus J minus minus, right? So I pair these two. Then I do I plus plus and J minus minus. So I go back, right? So I'm doing I plus plus and J minus minus. So that's why I can keep pairing, basically the way we have done. If it's already done, I can break. And otherwise, I can swap these two values. When I'm swapping the values, I should make sure that their answer also gets swapped, right? Like, sorry, the position also gets swapped because I'm using this function to keep track of the positions, right? So I have to make sure that the position also gets swapped. Also, I can mark that these values are done because they have reached their intended pair, right? They've reached their intended targets. So that's all. Just go through this code once. It's a bit dense, I would say, because I wrote it during the contest. I didn't write it like during a contest. Obviously, you're implementing quickly, right? So you can't see how clean your code is. So yeah, it is a bit dense. Just pause the video if you want and go through the code once, or you can revisit the code after the video. All right. So now once my whole array is done, I simply need to calculate what my answer is. So I just take answer or p and I add that to the sum. I print this answer and also I print all the values, right? So that's it. This is just output part to print the answer. This is the main logic. And basically what it's doing is checking for each power of 2. If I start at that, I start reflecting, right? So I'm swapping I and j. Basically, I'm swapping the positions of I and j. I'm reflecting them along this power of 2 and I'm marking them as done. Whenever I hit another done position, I break. Okay. or if I ever go out of bounds. If I ever becomes less than equal to R, or J becomes, like if I becomes greater than R or J becomes less than 0, then I can stop, right? So this is one implementation. Is everyone clear with this? If you observe, the time complexity should be n log n itself, right? Each position is being visited once, and we're using a map, so that's why log n factor. Okay, right. Now, what is the second way to implement this? Okay, the second way to implement. Okay, so now the second way to implement this is basically, let's go back to an example. Let's take an example for n equals 9. Okay, so we have n equals 9. Let me just quickly write down 9 values. Right, so we have n equals 9. And now, as we said, we are pairing each element with its complement, right? So if you take this one's complement, it should be 0, 1, 1, 0. And as you see, this complement exists, so we can pair them up, right? So one way we can find the complement is to do XOR with 1, 1, 1, 1. Okay, do XOR with 1, 1, 1, 1, and we will find its required complement. Okay. Yeah, Markdown, I'm doing that, I think, in the current solution. So yeah, there are many ways to implement it, like I said. I just explained the one which I did in contest. As long as you get the idea and implement it, it should work. Okay, so now I'm doing this second way to implement. This way to implement has the bonus feature that it will easily be solving D2 as well. Okay, so now when we do XOR with 1, 1, 1, 1, all set bits are 1, we get this value, right? We get the complement. Now, if this complement is between L and R, if this complement is between L and R, that means it exists in the array, right? It exists in the array. So we can pair them up. Okay, we can pair them up. So I paired this with this. Okay, now I move to the next element. Again, if this one's complement exists in the array, so this one has a complement of 0, 1, 1, 1, right? And if this exists in the array, again I pair them up. So as you see, I have paired them up here. Okay, now this is already visited, so I skip that. They're already paired. Now I go here, I check its complement, and its complement will be 1, 0, 1, 0, right? But the issue is that this one's complement does not exist, right? This one's complement does not exist. So basically, instead of doing XOR with 1, 1, 1, 1, I can decrease my mask. I can decrease my mask, and I can do XOR with 1, 1, 1 now. Do XOR with 1, 1, 1. Okay. So now if I do XOR with 1, 1, 1, what do I get? I get 0, 0, 1, 0, and that exists in the array, as you can see. So we will pair them up. Okay, we'll pair them up. Similarly, here if I do XOR with 1, 1, 1, I get 0, 1, 1. So I can pair these two up. This will already be done. Now here, if I do again XOR with 1, 1, 1, I get 1, 1, 0. But as you see, that's already done. That's already used up. So we can't do that. We'll try doing XOR with 1, 1. And then this will give us 1, 0. But that's also already used up, right? So now we do XOR with the final mask, which is 1. Okay. Do XOR with 1. Okay. So now we get 0, 0, 0, and we pair them up, and then we are done. Okay. So this is the way to do it with like masks and XOR, right? And to find its complement. All right. So this also will pass, and it will have a similar time complexity. Okay. So now let's look at the problem D2. Okay. So problem D2, and it's very similar, except the only thing is L and R can be over a wider range. Okay. So let's have a look at problem D2. So problem D2 is the same, except L can be any value less than R, right? L can be any value less than R, and R has to be less than 2 times 10 power 30. Okay. And also, obviously, these will be too many elements to print, but it is guaranteed that R minus L plus 1, so the total number of elements over all test cases is less than 2 times 10 power 5, right? So the time complexity will not change. Like we still need big O of n or big O of n log n solution, right? And let us see if there is any issue with our original approach on this problem, right? Is there any issue with our second approach on this problem? The first approach will not work because while reflecting over powers of 2, you run into issue in cases like this. Like here you see, there are no powers of 2, right? And for example, in the case over here, um, for example, we have from 3 to 6, or for example, we have from 1 to 4. Okay, consider the case which we have from 1 to 4, um, or even the case from 3 to 6. Let's consider the following test case. Okay, so example, L equals 3, R equals 6. Okay, so the values which we need to rearrange are basically 3, 4, 5, 6, right? So if we use the power of 2 method, it's going to take 4. It's going to swap these two, and it will swap and it will get 4, 3, 5, 6. But then these two will remain untouched, right? These two will remain untouched, unpaired, and that's not what we want, right? That's not what we want, and that does not give us an optimal solution. Okay. What if we try the XOR method? Let's try to find the complement of this with, so what is the binary representation of 6? 6 is 4 plus 2, so it'll be like this, right? If you find the complement, it will be 0, 0, 1, right? That complement does not exist. So let's try find complement like this. Let's try find complement like this. And we get 1, 0, 1, which is 5. So these two get paired. And now we can move on to the next step. For 4, we need to find complement. 4 is 1, 0, 0. Again, we'll try to find complement with um, 1, 1, 1 first, right? And then this will become 0, 0, 1. Sorry, 0, 1, 1, right? And then these two get paired up. Fine. So we see that our this method works. Let's try it on another example again. Well, let's try it on another example again, and let's see how it goes. Um, let's try the example of 1 and 4. Okay. So L equals 1, R equals 4. What are the numbers we have? We basically have 0, 0, 1. We have 0, 1, 0, 0, 1, 1, 1, 0, 0. Okay. So if we try to find the complement of this, we get 0, 1, 1. We pair these two up. Similarly, complement of this will be like this. So we basically have the pairing 2, 1, 4, 3, right? As expected. Right. So far the XOR method seems to hold up. And so we can just try seeing if the XOR method passes this. So, and we can try coding the XOR method up. So I'll just show you the code. Okay. So basically, again, this very similar code. Obviously I did D1 first, then D2. So obviously this position array could have been optimized away, but I still have it. So answer of I stores the each value of the permutation. Position of I stores the position of each value. Okay. Then again, we have this done to show whether a particular value is done or not. And this output also remains the same. Once the permutation is made, I just find the OR and I print the answer. Now, what I'm doing is I'm going through each mask. I'm going through the values of L and R, and um, I'm if it's already done, I continue. Otherwise, what I'm doing is I'm finding the complement of it. Okay, I'm finding the complement of it. So mask equals 2 to the power n minus 1 for current j, right? So we're trying first larger masks, then smaller masks. Okay. So the mask will be equal to 2 power j minus 1, which will basically be like 1, 1, 1, 1. And then we'll try with 1 less 1 and then 1 less 1 and so on, right? I find the complement. So x XOR I will give me the complement of I. Complement of I. This is for all the values of I from R to L. Okay. Now, if this complement is less than L or greater than R or already done, then I can continue. Okay. So obviously, invalid complements not allowed. Not allowed. Right. And then if the complement is valid, then I can say that this ith position is done. This complement is also done. I can swap these two positions and I can swap the elements themselves, right? So I'm marking them as done. I'm swapping their positions. I'm swapping the elements themselves, and that's about it. I'm checking with larger complements first, then smaller complements. One question you can have is why is this loop outside and why is this loop inside? And the simple reason is first we should check larger complements, then smaller ones. Otherwise, it can throw some errors, like some incorrect results in some cases, because the larger bits dominate, right? So the larger masks correspond to larger bits. So that's why if we have this in a different order like this, then it won't work. Okay, so wait, the code is kind of a bit off, but yeah, right. Wait, I guess the input is off. Let me just copy the input again. Right, right. So if I swap these two, what happens is basically some test cases give me the wrong answer. So for example, um, the last test case is giving me a wrong answer. And the reason is that if you take the last test case, we basically have some very large number of bits. Okay, some very large number of bits. And then um, this ends in, let's say, something like this. And then this value ends in, let's say, like this. And then this value ends in something like this, right? And so now if we try to pair this one up, we see that its complement does not exist with 1, 1, 1, 1, right? And we see that its complement does not exist like this, right? This value does not exist. Similarly, we try this complement and that does not exist. Then finally, we try this complement and we pair these two up, right? We end up pairing these two up. And the reason this will not work is because it's always better to pair a larger mask first, right? So this 1, 1, 1 can be paired with this first, right? Because these number of bits are larger, right? This mask, if you take complement with a mask of size 2 to the power 4 minus 1, right? Here we're taking complement with mask of 2 to the power 4 minus 1. Here we would be taking complement of 2 to the power 1 minus 1, right? And it's obvious that this is better. It's obvious that this is better because it has a larger mask, so the larger bits will be set. So it's better to pair these two rather than the last one. So it's basically better to pair these two versus pairing these two. Okay, pairing these two is giving us a worse solution because these bits have more priority than this bit. Okay, this bit's complement has more. These bits priority has more complement than this bit's complement, right? So that's why the order of these loops matter. We should first try larger masks, then smaller masks. We can't just for each element try whichever mask works. Okay. So first we'll try for all elements a larger mask, then for all elements a smaller mask, and so on. Okay. So it's important while implementing this. Try larger masks first. Wherever they work, you do the swap and you mark as done. Then, for example, a smaller mask, then a smaller mask, then a smaller mask, right? And what is the time complexity of this? Like we need to try all the masks one by one. The total number of masks is 30 since it's 2 to the power 30, right? So the time complexity of this would be big O of 30 times n, right? And since we're using a map, we can add a login factor. But obviously, if you implement this better, it will not take a login factor. But here we're using a map. So this is the time complexity. And for 10 power 5, this is way within constraints. Okay. So that's the solution. Simply just observing that in this problem, we need to pair with the complements and figuring out how exactly to implement it, right? So if you did the complement method directly if you did the XOR method directly in D1, then solving D2 would be pretty trivial as well. How to solve with try? I'm not exactly sure how you can solve with try, but yeah, obviously XOR tries exist. So if you have 0 and 1, like you want to pair with the opposite value, so you can directly find the complement that way. So yeah, you could solve this with try, but it would be a bit complicated, and I didn't think of it much, so I don't want to get into it right now. But yeah, a gut feeling tells me that might be possible. Okay, then we reach the end of the session. Any doubts you can ask regarding these last questions, C, D1, D2, or if you have any general doubts, those work as well. Okay, doubts. Any doubts, please put them in the chat. To be honest, the session already is reached 12:30, so We'll just take max 1 or 2 doubts before ending it. Any doubts, chat? Got stuck at C because I didn't try more test cases. Yeah, I guess C was again pattern observation. A lot of these questions today were construction pattern observation. So you should have tried some more test cases. Like for example, if you had tried enough test cases, then you would be able to spot that for stable patterns, we have to fix each value at 1 should be equal to itself. And once you realize that, the rest of it also becomes pretty simple. These values should be smaller and these values should be larger than the 1. So yeah, definitely do try more examples. Definitely do try more examples. Okay then. It looks like we have come to the end of our session. Thank you for watching. Hope you learned something. If you didn't get the code, then definitely do pause it. We'll be uploading the code to the YouTube description soon. You can go check it out, right? Thank you and see you next time. Bye bye.